Yes, sir. You are live, sir. You can interact with the learners.
Yeah, now I am doing that. I just probe.
Yeah, yes, sir. Just mute that YouTube video. That's and you can interact with learners.
I just
Yeah, yes, sir. Just mute that YouTube video. That's it. You can interact with learners.
okay. I think that there are not any questions. I think probably everybody's happy with the videos. Clear? Okay. I think that there are not probably everybody's happy with the videos. Can you hear me, people? Can you hear me?
Sir, I think without headphone sound was better, sir.
Oh, is it?
Yeah.
Okay, and I removed them.
You can, sir, disconnect that headphone. And sir, hope you have mute that YouTube video.
Which one?
YouTube video where queries are you able to see. Sir, your mic is off. Sir, your mic is off.
Yeah.
Yeah.
I think people are able to hear me, but I think there seems to be no question. So, where is the mic on? I mean, where is the mic coming here?
I think, sir, your YouTube that YouTube video is playing. You can mute that.
Where? YouTube.
Where the queries you are able to watch. Beside that, there is a YouTube video playing. You can down the volume of that video. Where playing option. Beside that, there is a volume icon. You can mute that. You can.
I don't think it is a mute, right? It's okay. I don't see any problem here. It is all unmuted only.
Beside that, there is a YouTube video playing. You can.
Yeah, that is all. That is fine. I've already unmuted.
where playing option, beside that there is a volume icon. You can click that.
Okay, gentlemen who are and women rather. Anybody has any questions? You either put in the chat box. Otherwise, we are going to close it in about 5 minutes. Anybody has any questions? You either put in the chat box. Otherwise, we are going to close it in about 5 minutes.
Hello, sir. Is your voice is repeating? Learners are getting repeat voice. Maybe because of the YouTube video.
That's what I've been telling so many number of times to you people. No, you don't listen at all. Yes.
Sir, where you are seeing watching the query, beside that there is a video. Please mute that video. So you need to go to YouTube. Sir, you can click on YouTube. Sir, please please go to YouTube. You did not click on YouTube. Your
Now,
presentation is open till now.
this is not this presentation you can't see.
Yes, sir, I can see presentation, but you need to go to YouTube to mute that video. Click on sir YouTube tab, browser tab.
Your voice is keep repeating here so many number of times.
Because sir, that YouTube video is playing back at background. That's why. Sir, are you able to see the queries of learners? Few of learners posted the query.
Getting confused. Totally getting confused. But I got into some other place now.
Sir, you can address the query which are asked through chat by learners.
No, it is not writing here now. I have no idea what goes on. See, it was writing before. Okay, so you can hear me?
यहाँ सर को बोल रहा हूँ कुछ सर समझ में नहीं आ रहा है सर को बोलो सर अभी प्रेजेंटेशन ओपन करके रखा है बोल रहा हूँ
Okay, there's a question by Raghav. How the passive current, current density, I suppose, right? Or how the passive current influences rise and
करते भी नहीं कुछ सुनते
Aqueous corrosion.
रहते हैं अभी रिपीट आवाज आता है अभी सर सुनते ही लेकिन कुछ करते ही नहीं क्या करने का मैं म्यूट किया है, वो रिपीट आ रहा है पिछले टाइम पे वो। जस्ट सेकंड में ट्राई करता हूँ, तब तक आप आपको जो क्वेरी चाहते हैं रिस्पॉन्ड कर सकते हैं। ठीक है।
Yeah, you can hear me. The only thing is it keeps giving a lot of echo. Okay. Let me just start with Raghav's question. That is how the passivation current influences crevice and fitting corrosion. Okay. Now, the passivation current, okay, if the passivation current is lower, okay, and the fitting corrosion and crevice corrosion would decrease. But there is a caveat. The caveat is as follows. The crevice corrosion comes into picture if the critical current density, repeat, the critical current density is very high. If the critical current density is lower, then the alloy remains very passive. Okay? So if the alloy remains very passive, the dissolution rate is equal to passive current density. So lower the passive current density, lower will be the dissolution rate, first of all, no doubt. But in a crevice, can the passivation occur or not? In a crevice, the passivation can occur provided the critical current density required for passivation is lower. It must be able to spontaneously passivate. And the second point about the ability of the crevice to resist crevice attack would also depend upon the dissolution of the metal, even without the passivation. I'll again explain what it is. For example, suppose I take 304 in the steel, and to that I add molybdenum to this. You will notice that the passivation current density is not going to significantly decrease. But what decreases is the critical current density. Now, along with that, the alloy acquires resistance to dissolve actively. That means if I remove the passivation, expose the bare metal, maybe in acid, suppose I take a very highly concentrated hydrochloric acid. I don't allow the alloy to passivate. The alloy will have lower dissolution rate if you have molybdenum. That means whether a given alloy will resist pitting corrosion, crevice corrosion, once they are formed, will depend upon within the pit, within the crevice, how much the metal will able to resist corrosion. Because in the pit, in the crevice, the pH of the medium, the chloride content, all changes. The chloride content will increase. The chloride content will increase. The pH will decrease. So the metal will become highly corrosive. I mean, it corrodes. So the ability of the metal to resist pitting corrosion and crevice corrosion will depend upon how much the metal will able to resist corrosion in acidic and chloride solutions. Now there is one more. I think Avijit is asking a question on what is the difference between pitting corrosion and crevice corrosion. Okay. I hope you are able to hear now properly, right? Okay. Now the difference between the pitting corrosion and the crevice corrosion is follows. It depends upon the initiation of pitting and the crevice corrosion. Pitting corrosion initiates when the film breakdown takes place, generally occurs at very positive potentials. And the potential is going to be positive. The crevice corrosion generally occurs at a relatively negative potentials. You remember a active passive transpassive curve, and if you are going to draw a cathodic line, if the cathodic line intersects the nose of the curve, which means the I critical is higher than the current corresponding to the passivation potentials, cathodic current actually is not going to pass away. So in a crevice, the potential is generally starts with a relatively negative potentials. In a pitting, it takes place because of film breakdown, and the potential is normally going up. That's the way normally that it happens. So that is the difference between pitting corrosion and crevice corrosion. The other difference also is the crevice corrosion is macroscopic, right? I have a flange joint, and within the joint, the access to oxygen is reduced because the diffusion is controlled. The oxygen does not reach the interior place. The crevice starts. Pitting corrosion is mostly microscopic. There is film damage that occurs maybe because of chloride, maybe because there are you rise of potential, and so the film breakdown takes place. So macroscopic I would consider as crevice corrosion. Microscopic I consider as pitting corrosion. So this is what I think you should be looking at. So the resistance of the metal to crevice corrosion and pitting corrosion is somewhat related to passive current density, because we normally say that when passive current density is lower, the alloy also dissolves at a very low rate, even when you remove the passive current. So that from that way, you can say that it is related to each other. I hope that the point is clear. I think if Raghav has still a question, you can type it out. The next one is please explain about exposure time and potential current relation in case of pitting corrosion. Okay. Now we all know what pitting is. Pitting is a stochastic process. It's very important to understand. It is also spatial. It's a temporal also. Now, you know very well that a potential dynamic polarization curve, right? When you draw a potential dynamic polarization curves, unfortunately, I'm not able to draw here. Okay. So if you look at the potential dynamic polarization curves, you will see a pitting potential. At that potential, the alloy fits instantaneously. Doesn't take much time. Suppose I carry out the same study at a very slow scan rate. The scan rate I'm going to use is, let's say, about zero point 0.1 millivolt per second. At lower rate, I'm just rising the potential. The pitting potential now start decreasing. So the pitting potential so obtained is a scan rate dependent. So what does it really mean? It means there is one thing called a time dependent process. Now, why does it happen? It happens because pitting again is a kinetically controlled. How does pitting occur? So one easy way of understanding is the chlorides get absorbed on the surface of the oxide film. They migrate inside and then they damage the film and attack the base metal. It takes time. Now it takes time for the chloride ion to migrate from the surface to the film to the substrate and get attacked. And which time then you find the current is increasing. The increase in current is a reflection of metal undergoing pitting. Right? So there is a time lag for that. Now, what else contributes to it? For example, I increase the chloride content more and more. Then the time taken for the chlorides to migrate across the film to the metal surface decreases. The pitting tendency increases. What also I can do, and I apply the potential now. I am going to slightly increase the potential. There's a driving force for the chloride ion because you are making the potential relatively positive. You are anodically keeping there, right? So when relatively positive, then the tendency for the chloride to get into the oxide film and then reach the metal surface is increasing because chloride ion is negative and you are relatively increasing the potentials. The chlorides migrate to the films. So the tendency to pitting is increasing. So the another driving force for pitting is the applied potentials. And the potential is increasing, more chlorides will drive and go to the surface and start pitting. So there are factors: what? The chloride ion concentration, the potentials, the time. All three are related to pitting now. So what does it mean? Suppose I want to, take certain concentration of chloride. For example, I take 0.1 molar sodium chloride. And I want to increase the potential towards anodic direction by about 100 millivolt. And let's say that it is taking about 10 minutes to pit. Now, the same 0.1 molar concentration, if I keep the potential about 200 millivolt, now the time can be significantly reduced because the driving force is very high. Alternatively, I keep at the same 0.1 volt, that is 100 millivolt. I'm going to increase the concentration, let's say from 0.1 molar, I'm going to go to 2 molar concentration. The time taken for pitting is decreased now. So, pitting is a time dependent process as much as potential dependent, as much as chloride dependent, because it's a kinetic phenomenon that we talked about. Okay? So that is how we can say that exposure time, potential are very important and that decides the pitting. And that also decides your current also. How do you know it is pitting? The only way that you know is that there is increasing current. If the current is not increasing, then you don't say there's a pitting taking place. So current is the measure of localized attack taking place on the metal. Okay. And I hope you understood this thing. If you have questions, VJ, right? I think please let me know. You have still question you need to be clarified. You let me know about it. Okay. So yeah, I will come back to you, Praful. Okay. Let me go to the other question. Raghav, is zirconium and titanium behave the same in galvanic corrosion and seawater? I really don't know what you really mean by that, actually. Okay. And whether you are talking about connecting zirconium to steel, titanium to steel, or zirconium and titanium. What exactly you mean by this? Can you just clarify this, Raghav? Raghav, are you online? Can you elaborate this question? Is zirconium and titanium behave the same way? Yeah. Can you just elaborate on that question? See, the one of the important thing about galvanic corrosion, let me try to reply in a different manner. Okay. One of the reasons why the galvanic corrosion occurs. Okay, okay, yeah, that's great. Yeah, you can phrase your question. You think about it. Now, meanwhile, let me answer Praful question. Yeah, good evening, Praful. Your question is: can pitting corrosion takes place in titanium in seawater, and is passive potential important parameter to be considered while developing the alloy? Okay. Yes, titanium does not fit in seawater in the normal conditions. I'm talking about ambient temperatures, let's say 40, 50 degrees Celsius. The titanium does not fit. The breakdown, the oxide film is very, very strong. So it does not fit in seawater. Okay? But if you raise the temperature about 100 degrees or 200 degrees, something like that, okay, and you put a salt, heating takes place. At ambient temperature, near ambient temperatures, titanium does not fit in seawater at all. Now, the second question is passive potential important parameter to be considered while developing the alloy? Yeah, the passivation potential, of course, is very important in developing an alloy. The passivation potential, if it is going to be lower, more negative, I put that way, in simple manner, right? Then it is good. So what does it mean? If you look at the polarization curve, the anodic polarization curve, if it shows active, passive, transpassive dissolution, and you know that it goes to the critical current density, and just above the critical current density, the current again becomes very low, and that current becomes a passive current density. And that is the potential we call as a passive potential. Now, if the passive potential is lower, is very low, what does it mean? It has ability to passivate much easier than having a higher passive potentials. Because if I have to have a higher passive potential, then the cathodic reaction, right? How does this spontaneous passivity occur? The metal should have a spontaneous passivity, right? The spontaneous passivity occurs because you have a cathodic reaction, and the cathodic reaction, it has its own Tafel lines, its own Tafel curves, and that cathodic Tafel line should not intersect the nose of the active, passive, transpassive curve. That is possible very easily if the passive potential is negative, right? You have because at lower passive potentials, you will have larger cathodic kinetics, isn't it? Because you are having more over voltage. So if you use the active, passive, transpassive curve and you draw the line, you will know that when the passive potential is lower, the same cathodic curve will show higher current density, the passive region. So spontaneous passivity becomes much easier if the passive potential is going to be more negative. It certainly is good. So that is possible only when the oxide films are formed at a negative potentials. I don't know if you have seen the passive, the polarization curves of pure iron. The pure iron you take and you carry out the potential dynamic polarization in sulfuric acid. It does show a passive, current. Actually, it does show passivation, but the passive potential is quite large. Okay? You need to go to very high potentials. So iron does not become passive because you need a cathodic reaction which is of very noble character. Acid cannot passivate at all. So having a low passive potential is very good, and that is supposed to be spontaneously passivating alloy. Actually, yeah. I hope that answers your question, Praful. If still you have a question, you are not clear, you do, please let me know, and I can elaborate further on that. I think now I have again question from VJs. You as you explained, chloride content is responsible for pitting. Just a practical case comes to my mind. If I put salt in stainless steel household utensils, is there the pitting corrosion? Yes, the household utensils. When you put a salt, if you're going to put a salt, what do you mean by that? Suppose I'm going to store the salt. I put that way. Suppose I take a Tata salt or some other rock salt. I store it in your stainless steel vessel, for example. It will go to pit, right? Because the salt concentration is quite large. But you are going to take a water, let's say tap water. The tap water does contain chloride, isn't it? It doesn't pit. Why it doesn't pit? Because the chloride content is very small, very low. It does not pit. Actually, pitting is a little complex process. I didn't really spend too much time on it. Actually, in a system, let me just spend some time on passivation. Okay, then you probably will understand what it is. But if you look at the polarization curve of a stainless steel, you see a region which is called the passive region. What is the passive region? The passive region has a definite amount of current, maybe 1 micron microamperes or 2 microamperes. That means when metal is passive, still there is a dissolution taking place, right? So that the current is still going through. How does it happen? It happens because that there is a film breakdown takes place, small breakdown, and again there is a repassivation. So in most cases, you find when it's talk about passivation, it does not mean the passive film is so stable once formed. It's not like that. The passive film slightly gets damaged, reforms, gets damaged, reforms. So it's a dynamic process. The passivation, as you notice, is there is a current that is moving. That means it is still there are dissolution taking place at local areas. But it does not lead to a stable pit. We call them as metastable pitting. Okay? So there are small damages happening to the metal surfaces. Okay? There are small damages happening to the metal surfaces, but it heals out. That means the metal is always active. There is always dissolution process that does not lead to pitting. It is like you slightly damage it, it starts healing out. So healing is as good as damaging surfaces. So normal pitting does not mean that there is no dissolution at all. There is dissolution, but that dissolution is very insignificant. It is able to repassivate again back into the crevice. Okay, so that is what it is. This is like, for example, you fall down, there's a bruise, it heals out, no problem. It's a deep cut, it requires medicine. You have a problem at all, actually. So all the passivation that you're seeing there, it does not mean there is no metal dissolution. It does not mean the film is always stable. The film is undergoing some kind of dissolution process, repassivation, all this happens. Once the stability is lost at some location, the pitting starts actually. So that's what I mean by. So when you're going to add more chlorides, yes, you are going to now start damaging. That means you have for example, you take your hand, you start rubbing like this. You have a little bit of, you apply more pressure. You take emery paper, start rubbing. You take coarse paper, start rubbing. And you take much more coarse paper, start rubbing your skin. You find start pain taking place. So it is essentially means very similar to that. Okay, you are going to have more and more aggressive thing. For example, same chloride, I decrease the pH. Pitting of course more. Okay, so because pit becomes stable when the pH is lower, that you have seen, right, how the pit is going. So within the pit, it becomes more acidic. So the ability of the metal not to have more chloride in the pit, not to have more acid in the pit is what happens. So pitting mechanism is more complex actually. And so, that means you need to be understanding several kind of things, but I give you a broad picture about, how things happen. So you are going to put a salt in utensils and leave it for a longer time, you're sure you're going to get it. In fact, you also know there are different types of stainless steels. Some of the utensils are made up of what? It's made up of arsenic grade stainless steels, but they do not have adequate nickel, they add more manganese, and you find that they undergo more corrosion than normal 304 stainless steels. But you are going to have 316 stainless steels. Yeah, it can tolerate more amount of chlorides. So there will be a pitting can happen at all. But this question is not very, you can't have a blanket question. The question has to be, what is the salt concentration? What is the temperatures? How long I am going to keep? All are going to be important. Or you take simply a utensil. For example, you take a stainless steel utensil. You put a little bit of salt solution. Over that, you put a small glass plate. Below the glass plate, you see crevice corrosion occurs there itself. You can try it out in your home by slightly increasing sodium chloride concentration in a water. Allow it and see that it takes place or not. In another case, you put a plate on it, right? You observe both. You see that rust takes place. A place where sodium chloride is added, slightly the plate is kept. That one will show more rust, quickly rusting. Then you have the same sodium chloride concentration, no plate on the surfaces. It is better actually. So the crevice corrosion is more dangerous as compared to pitting corrosion because crevice leads to accumulation of salts, accumulation of chlorides, then accumulation of the acidic conditions, which is not happening in normal pitting conditions. Of course, when pit grows deeper, it becomes like a crevice. it becomes more dangerous. Okay? I hope the point that I made is you can understand it. But yeah, I'm pitting is a big subject that I think we need to be taking nearly maybe an hour or two lectures, 2 or like 3 lectures to clarify the mechanisms. But I've given you a very simplistic picture about what it is actually. Now you also asked a similar question: what surrounding conditions will accelerate this pitting? I don't know what. Can you elaborate on what you mean by what surrounding conditions will accelerate pitting? Can you elaborate on that? So meanwhile, let me go to the next question of the Raghav, who has rephrased his question. Is galvanic couple titanium platinum, zirconium platinum reduction occurs in the same way? Fantastic. Yeah, it should actually, right? When you take titanium and platinum, zirconium and platinum, I think you should have reduction in the corrosion rate. Same way it happens in titanium. The reason is also you've seen, right? I also drawn. It's a very interesting question. The answer also can be very interesting now, right? See, it's always fall back on the fundamentals. You go to the Tafel curves. You go to the Evans diagram. You draw the Evans diagram for titanium, right? You also draw the Evans diagram for zirconium, right? If the zirconium Evans diagram, that is the anodic potential curve, looks like titanium, or even better than that, platinum certainly will give rise to reduction in the corrosion rate. I do think so, that platinum will also reduce the corrosion much the same way. Platinum reduce corrosion of zirconium much the same way platinum will reduce the corrosion of titanium, because you need to have galvanic couple in order to passivate it. Platinum facilitates passivation of titanium, right? Platinum facilitates the passivation of zirconium, right? What is the cathodic reaction? Please notice the cathodic reaction here is hydrogen evolution. Zirconium was said, that's why look at here this case. In this case, the passive potential has to be lower than the equilibrium potential of hydrogen. So there is a question by earlier by someone asked a question, right? Same. Let me just go here. Who was it? Okay. Yes. The question earlier. So the profile, right? It's passive potential, right? So the passive potential is important, right? So in this case, titanium passive potential is so low that hydrogen reduction reaction can spontaneously passivate. That's why. In fact, this may not happen with the stainless steels. The stainless steel, probably you are going to couple with the platinum, it may not passivate at all, actually, right? It's very unlikely it may not passivate at all. Stainless steel cannot passivate. Why? The passive potential for stainless steel is relatively noble. Okay? So there you need oxygen content. When you have oxygen content, what happens? Oxygen content, the redox potential for oxygen is quite large, plus 1.23 or something like that, right? So you should be able to, the cathodic curve is much higher than the passive current density and passive potential for the stainless steel. So it's possible that in the case of stainless steels, you couple with the stainless steel and platinum, you may get a problem. But in the case of titanium, you may not get a problem because the passive potential for titanium is so low it can happen at all. Yeah. That's good. Yeah, Vijay, fine actually, yes. Okay. That's good. Yeah. Okay. So Vijay is okay. So Vijay, you don't have any questions further, right? Okay. Yes, great. Now let us go to the profile. And what about passive current density while developing alloy for pitting corrosion? Whether it is important parameter to be considered. Actually, it is important only to a certain extent. Actually, it's only to a certain extent is very important. For example, let me take two alloys. One alloy has very high pitting potential and also has higher passive current density. Right? The other alloy has got lower pitting potentials, but very low passive current density. Understood? First alloy has got higher pitting potentials, right? And higher passive current density is also higher. Okay? The second alloy has got lower pitting potentials, but very low passive current density. Now you take both the alloys, in the normal conditions, the alloy with the lowest passive current density will corrode least, irrespective of the pitting potentials. Because the passive current density is almost equal to ICAR, right? If you are going to look at the Evans diagram, the passive current density is equal to the ICAR, isn't it? That is what spontaneous passivation really means. Right? I wish I could draw it in the board. Okay. So, from the corrosion point of view, the lowest passive current density one will give you the least corrosion. But let me take the pitting point. Suppose between the two alloys, the alloy having the higher pitting potentials and higher passive current density, and another case, the alloy having lower passive current density and lower pitting potential. Suppose I bubble with oxygen now. I'm going to bubble the solution with oxygen now. So what will happen now? The potential, the corrosion potential will move up. It keeps on moving up, moving up, moving up. But what will happen now? The alloy with lower pitting potential starts corroding at a high rate. The alloy with the higher pitting potential will corrode at lower rate, but still determined by what? By passive current density. So the ECAR value goes above pitting potentials. That's a problem. So answer to that is, in simple terms, I put it this way: as long as ECAR is lower than E pit, I repeat, if ECAR is lower than E pit, then lower IP is very good. If the ECAR is higher than the E pit, then it's of no use at all. So as long as our ECAR is going to be lower, then lower IP is very good. If the ECAR is exceeding because some reason, so you add an oxidizer, for example, you add an oxidizer. You know, for example, like you bubbled with oxygen there, or rise temperature, for example. That's the problem. So that is the key issue here. If you want, I give an example. Let's take the example of titanium, aluminum, stainless steels. Okay? Aluminum will have reasonably better passive current density compared to stainless steels. But aluminum is more susceptible to pitting. Why? The pitting potential of aluminum is lower than the corrosion potentials in normal water. In a normal water, okay, stainless steel is better. But take titanium. Titanium is very good in normal water, in seawater, because it has got lower passive current density, it has got higher EPIT values. So, if you want talking about alloy development, the best thing is what? The best thing is having higher EPIT value and lower passive current density. Both are very important. But generally, a passive current density of the order of 1 microampere will give you 0.5 MPY. You're talking about a stainless steel. So 1 microampere current is considered to be 0.1 MPY. So it's going to give you a huge amount of time. So it's not really a problem at all. Okay. So put that way, you want to have a good alloy, the best alloy, suppose you think about it, then the alloy development should involve what? As low a passive current density as possible and as high a pitting potential as possible. That also means you're going to increase the cost of it. You're going to increase chromium so much, you're going to increase nickel so much. So see, these are not going to come for a song, right? That means these elements have some kind of behavior. In fact, I mean, one way, of course, to do is add cheaper alloying element. The cheaper alloying element like nitrogen. In stainless steel, for example, they add nitrogen to it. A small quantity of nitrogen. It gives you lower passive current density, gives you higher repeating potentials. Good, no problem. But some cases it can work better actually, both ways. So some cases, not the same element can give you both properties. It may give you better pitting resistance, but it may not give you lower passive current densities. Okay, so yeah, you want to have an ideal alloy, you have to have both low passive current density as well as higher pitting potentials and also lower passive current potentials, right? So this is an ideal alloy that you like to have. And again, you must have hysteresis. For example, you've seen that you are going to reverse the polarization curve. Okay, you increase the potentials and draw the polarization curve. So you reverse it. You should have higher repassation potential, right? Higher repassation potential also means what? It means that the alloy, even when it's pitched, is going to be stable. That means you should also have higher ERP. Repassation potential is also equally important because sometimes you may have a higher pitting potentials, which means initiation of the pitting is very, very difficult. But sometimes when you initiate the pitting, growth of the pitting may be in worst case. That's also you don't want, right? So you want to have high pitch, high repassation potentials, and you also want to have very low IP value. You also want to have very low passive potentials. So that defines, an ideal alloy that you can think about. Titanium is one such alloy you can think about. As Praful, you still have a question? And Vijay, is your, I think all your doubts are clarified about pitting temperature and, and other responsible factors. Yeah, that means we have to increase the passivation. That's it. Yes, and see, but again, I will tell you. For example, there's no point in increasing chromium beyond 20%. Right? Why would you do it? But you do it provided if the environment is very bad. There are cases where the environment becomes so aggressive. For example, some geological cases where the temperature below the sea, below the earth is very large and you have high chloride content. Yes, there I think people go for high chromium content and stuff like that. Okay. But again, one is about our development, other is about using the alloy judiciously for particular purposes. So you want about impedance measurements? Can you explain for the corrosion rate determination? Okay. Well, of course, it's a big story, and let me try to simplify it as much as possible. See, before you use a technique, you need to be asking yourself, what I'm going to get out of it. If I have to spend, let's say, 1 paisa extra for anything that I buy, I look for, does it really deserve to be? That is the primary question that you ask in corrosion testing and evaluation. For that matter, any testing and evaluation. It is very important to do that. Now, the question now we are going to ask is, you want to determine the corrosion rate. I want to use impedance measurements. That is going to be very, very, I would say that if I have to tell my students, I would say, please don't use impedance spectroscopy for determining corrosion rate. I would first of all say that please use weightless measurement. First of all, it's so direct. You don't have to know the table relationship. You don't know anything at all. the corrosion rate so measured is so direct. No one can challenge it. No one can challenge. The values are real values. But then why am I going for polarization measurement? What is the reason for that? The reason for that is, suppose I do a weight loss measurement. If I get some corrosion rates, some X, Y, Z, I want to know why that happened. The weight loss measurement does not tell me why does it happen. It only tells me that there are different corrosion rates. So if I want to know the mechanism, if I want to know something more about it, then I go for polarization studies. So I carry out polarization studies, I look at the tablet slope. Just now we talk about passivation, for example. So all we start understanding the behavior, corrosion behavior. From that particular point of view, the DC polarization experiments are very valuable as compared to weight loss measurement. It does add a lot of value. But it comes out with a lot of uncertainties now. I don't know how many of you have seen the polarization curves. Sometimes when you do a polarization curve measured in the laboratory, there is no clear taper line. Oh, there's a problem. You don't know how to measure, how to determine the car. I mean, I will not do it if there's no taper line. But there's no hesitation in the weight loss measurement. Simply, I take the weight and measure it, I get it. But in a polarization curve, if the taper lines for cathodic and anodic are not clear, then I don't think that polarization curves are going to be useful for determining the I power value. And so I cannot use it. But of course, still is useful. I mean, I'm not saying that all the polarization curves are determined only for I car determination. But still, we can give information about how the anodic curve looks like, how the cathodic curve looks like, and so what happens. All this is possible to look at it. So I derive more information from polarization curves than what I would do with a simple weight loss measurements. So that is an objective of doing that work. If somebody does weight loss measurements and polarization measurements, give same kind of information, I think that guy should be really kind of wasting his time, wasting resources. He should go beyond what you get from weight loss measurement. Now let me come to the impedance measurements at all actually. Why would somebody go for impedance measurements when you have a DC polarization, right? Now, for the DC polarization, one of the problems with the taper lines are it is the destructive test. One problem that we're going to get out of that. But again, you want to avoid destructive test, I go for linear polarization, where the voltage, I apply very small, about 10 millivolt or something like that. I'm really not disturbing material, and so it is a non-destructive test. So I can use this measurement at all. I think much more simpler, There I stand their equation, and there's nothing more to really worry about it. Relations are very simple. I can determine the I car if I know the RP value. Now, if I'm getting RP value from linear polarization, then why should I go and take the same RP value with impedance measurement? It becomes too, wasting. You are asking for an elephant to come and lift a small pin, right? So that's a problem. We won't do that. So one way to utilize is that what more do I want? For example, do I want to know that with respect to time, what happens at all? Or do I measure, for example, I use this coating. For example, a paint coatings I have. You cannot use DC polarization paint coating because paint coating is a capacitive function, right? It doesn't allow the current to flow, and all your Butterworth equations, capital equations are not going to be valid at all. So I cannot use it. I have simply not possible. So for a paint coating, I normally use impedance spectroscopy because that's the only way that I can do that. And not only that, I will get a lot of information. The information about how much water has gone into that, the breakpoint frequencies, the quantity of water that goes into that actually, and all a lot of information is going to get out of it. So the impedance measurements, in my view, should be used to gather more and more information about the corrosion processes than simply getting the weight loss. That should be the basis of using the impedance spectroscopy. Otherwise, you are going to have a lot of problems. In fact, you may get a result which is not really exactly matching with weight loss measurement at all. Because the relationship between what you measure and what you interpret is going to be complex. Okay, so this is what I would like to say. Otherwise, you can simply get an RP value, fine. Okay, the way you do that, you fit the curve and using some bundle circuit, whatever kind of stuffs, and get RP value. The RP value is similar to RP value measured from linear polarization. Steiner equation is valid or finished. No problem at all, actually. So, no issue at all in this case. But what the problem is, we don't know what the taper lines are, right? The taper slopes are not known, so we won't be having a problem in getting exact ICAR values because the taper lines can keep changing. That are some of the problems that you have in linear polarization and as well as in the impulse measurement. Because you change the taper slopes, well, ICAR changes, right? You may have same RP value, but does not mean they have same corrosion rates. So it can happen from that way. Okay? I have just given you a broad thing, but otherwise you need to know more about impulse spectroscopy, separate discussion required on that. Yes, Raghav, you have a specific question, you please pose. Okay, so the profile has this question: if I want to select a material for study of galvanic corrosion in nuts and bolts, which material would you like to suggest that I should select for nuts and bolts? See, well, I mean, it's a very broad question that you're talking about. I don't know what is the and what you have in mind. That I'm not very clearly what you have in mind. See, there are nuts and bolts of stainless steels. There are nuts and bolts of titanium alloys. There are nuts and bolts of even brass, copper alloys. All are there actually. All kinds of things are there. So we normally use, same material as the sheet, right, where you want to join them, right? So the nuts and bolts should be of the same material as that of your basic structure, so that the galvanic corrosion can be reduced. The question that you would like to know, I don't know whether it is that. Suppose I have, because sometimes ideally you can't have same material. That's not possible, right? Industrially, that's not very possible. I have seen cases like, for example, the fasteners, you must have relatively higher strength as compared to the sheet, for example. So compositionally may be different. If not compositionally, microstructurally they can be different. You may give a different heat treatment, all kind of stuff. Now, if for some reason you cannot choose the same material, you have to choose a different material. That happens in building, for example. The filler wire is not going to be exactly the same as the base metal, right? It's not exactly the same. There is a small variation. Okay? Now you may ask the question that if I am going to choose a different material, small variation. Obviously, you can't choose a wide material, right? Because if you do that, then obviously you are going to have galvanic corrosion. I mean, then you will say you are not a good engineer. You are going to choose a random. So you are not going to do that. In practice, you always choose which are very close to the galvanic series. That's what the galvanic series talk about. But ideally speaking, you should have the same material, which is not possible, right? You are going to have different material. Now the question that you may ask is, oh, I'm going to use slightly varying thing. So what is the galvanic corrosion I'm going to get out? Okay? So then you can do galvanic corrosion. You can do polarization curves. You can use zero resistance ammeter. Okay, and all is possible to do that. Okay, nuts and bolts used in trucks or heavy vehicle applications. It's very interesting that you see that is the galvanic corrosion is not something absolute. Right? Equilibrium potential is absolute value. Right? Standard potential is absolute value. Is corrosion potential absolute value? It is not. The corrosion potential depends on seawater application. Galvanic series. I don't have the data with me readily, but if as long as you choose steel versus steel is not a problem. If you're going to choose steel versus aluminum versus steel, like that, you're forced to do. Sometimes you don't have. Design engineer says, no, yeah, I cannot do.
I can't design it like this. You corrosion guys are stupid first. You tell whatever you want. Ignition in automobiles. People start aluminum in automobiles, because light, right? We cannot be corrosion guys cannot be stupid guys and go and tell the guy, no, don't use magnesium. That is not a possibility because he wants to do lighter. So use combination here. Now the question now comes is that how do you avoid galvanic corrosion? It's what? Because you know that galvanic corrosion won't happen. How can you close your eyes and say that, oh, magnesium is going to be compatible with steel? Is not compatible at all. But there are ways. We have also shown how to avoid galvanic corrosion from the point of an engineering perspective. How we can do that. We also shown how to do scientific perspective, how to do that. So, in my view, if we are going to talk about nuts and bolts of the same material, okay, even in the sense like, of course, I know that, they are slightly different in terms of steel, right? The steels in automobiles they're mostly interstitial free carbon. In interstitial free steel, right? You want a very flexible steel and nuts and bolts are going to be a high carbon content, maybe more. Then there may be a small amount of things can happen. But in my view, what happens is the galvanic corrosion may be less. I'm not saying don't study. I think you can study still. It may be less because these are all again treated with capacitating. Then you're going to apply some paint and all. So you see that a lot of the effect of so-called galvanic corrosion is quite a bit. They have been tampered. They have been tempered actually. Okay, so they have been brought down to this actually. So it's possible that they may not have galvanic corrosion at all. And again, the nuts and bolts are completely covered with paint. Then no environment goes, and so there's no problem. So I can couple, for example, magnesium with even with the platinum also, right? As long as I don't allow any environment, no galvanic corrosion. So if you're going to apply a paint and you're going to allow, you're not going to allow the environment to go and interact with this, again, the corrosion and galvanic corrosion to reduce. Okay, and to be sure, of course, you can study. Nothing wrong in studying this actually, because you want to be sure that you don't have the problem. The one way, of course, to look at the problem is looking at the old vehicles, where they've used. Take it out and see how the interface is getting corroded or not. The interface is not getting corroded, and I think then there's going to be no problem. Right? How do you analyze galvanic corrosion problem? Each failure leaves behind a signature. The signature for galvanic corrosion is interface between the dissimilar metal with corrosion, and one will be anodic, other will be cathodic, but all won't be. So that's the way you can also see if this, really having any galvanic corrosion at all. So some amount of, studying the field experience would help you out in tailoring the problem. So that whatever you see, after doing all the work, you want to see that your company is recognizing you. They don't want to waste your time. You wasted 6 months of time for this and coming up with no problem. What is so big deal about it? We do it as a researcher because we want to be sure about it. But the company guys may think other way around. I'm wasting all my time. Okay. So a bit of background, a bit of analysis of the field work will tell you how they are, and then you can tailor it to your work and see what really happens at all. And secondly, if the galvanic corrosion is so small, if the automobile is meant for about 10 years, you forget it. Now, I'm not really worried about it. So it's not a problem. Galvanic corrosion is not a problem because you are going to now simply take it out. It doesn't matter. I'm going to now throw the whole component. I don't care about galvanic corrosion because 10 years I'm throwing the whole thing out. Thank you, Praful. Yeah. Any other questions? Oh, thank you, Sandeep. Okay, so you finished your other course. Okay. Well, we are. I'm okay. Yeah. Thank you. Thank you so much. And if there are any questions, you feel free. And there are some questions regarding what should be the end semester exam model. I think I will do that. I think I'll send you one model question. But again, I cannot give you exactly a template. don't ask for a template. We're all asking. See, one way of looking is for you people to make you to understand is what the course is all about. The course is all about learning. The course is not all about grading. Actually. Grading is the least priority that I normally give to any kind of learning process. And so you don't worry about it actually. You should not worry about. Start learning as much as you can. Okay, but that is what is going to really help you, future in the profession. Of course, the marks, of course, I'm not saying they're not important, but it's very difficult. If I give a template, you prepare. You're preparing only for the instance and exams. You're not going to prepare for the course. So that is why I'm always afraid that I give a template. You always, whenever somebody teaches, you always look at the template. Oh, do I need to learn this or not? If it's not going to be there, forget about it. That is not the way a course to be learned. So let's not worry about it. Actually, whether MM699, whether is available for any chance in NPTEL. What is MM699? It's the coating it is? It's a coating course? I think the Sandeep or Abhijit may be knowing, right? What is this 699? Right now I don't remember actually what it is. Oh, corrosion lab. No, corrosion lab is not available in NPTEL. How do you do it? No, it's a problem, right? I don't know. The NPTEL guys will have a way of doing it. I think we can have it outside. We'll start recording it. Yeah? Yeah, no problem. Yeah, let's give some time. No problem. Okay. Okay. Let us see that because we have a course, materials characterization course, and that probably trying to see where maybe next year we'll run NPTEL course. Maybe I'll try to do that. Okay. So great, guys, and have a great weekend and enjoy the festive seasons. Okay, and be safe and happy, peaceful Diwali for all of you. Okay. That's good. I'm happy. Even then, less number of people is a good questions. That really talks very highly of you people. You really analyze the problems. You really not preparing for exams. You're preparing for yourself. That's a great thing. Like this. Thank you. Okay, so we can close this session now. Yeah. Thank you very much. Thank you. Thank you. Thanks for everyone. Thank Sandeep and Abhijit for arranging. And okay, of course, there are two Sandeeps here. Sandeep from NPTEL, Sandeep TA both. Okay. So thank you, Praful and Raghav. Thank you very much. Okay.